what we're looking at here, we're starting with confidence intervals for large samples. However, they're large samples. I should change this. It's to when the standard deviation is known. It's whenever the standard deviation is there that we're going to be able to do this. There should be a chart on your notes. Let me just see where my note page is. Let's see if it's on your notes. Huh, no. All right. Let's just talk about this for a second. The population, we write the population mean, we write the population standard deviation. For the sample, we write a sample mean, we write a sample standard deviation. If you're going to write a variance, population variance is your sample squared. Sample squared is here. So one other thing that we haven't talked about yet, when we do a proportion, this is a P. This is a P with a little hat over it. So these are the symbols that we're going to use. When we make some of these things, these guys are where your point estimate comes from. So when we talk about a point estimate, what we mean in a point estimate is something from our sample has to represent the population. If we're talking about a mean, we'll talk the sample mean. If we're talking about a standard deviation, we'll talk the sample standard deviation. So we have to have a way to represent the population when we do this. So what we're doing is we're making this inference about the population. So we're going to start off really, really simple. We need to know theta. This should say when theta is known. Okay. Now, again, our point estimate, this is really important, is that population parameter. In this case, we're doing mean. It's the x bar. The most unbiased point estimate of the mean is the sample mean, the x bar. So whenever we make an inference about your population, we'll base it on your sample mean, which makes sense, right? We've been doing sampling, figuring out the mean of the sample means and all of that other nice little things. So all they're asking you to do is to say, and we don't have to do all this, but we'll just make sure you know how to do it. On page 298, on example 1, they give us a bunch of data. How do they find the sample mean? How would you find that sample mean? And the standard deviation? Add them all together, divide by how many there are, but since I'm asking you to find the standard deviation as well, what would you do? Put it in your L1, and do a one-var stat, right? Would you come out with the mean and the standard deviation? So you're going to put it in your L1. I'm not going to ask you to do it because we already know how to do this. We're going to put it in our L1. We just list all the numbers. We do a one-var stat just for L1. And this is our mean. And our sample standard deviation is this. I think everybody remembers that, right? Yes? No? Okay. We don't have to practice doing that. All right. So that's all they're looking for you to do that. And then try it yourself. One, they're giving you a table on the left. Yes. Yes. Singing at the end of class because you finished. So singing at the end of class. All right, so now we're good with that point. We don't have to worry about that. All right, so we move on along here. A lot of this is stuff we've already done, but you have to remember that you're just making this inference about your population based on your sample information. So since the probability of finding any exact point is very small, very rare that we're going to hit that exact point, we can estimate that the population mean lies within a certain interval. And that interval is based on your sample. Okay, remember, because this is where we make an inference. We started making inferences about your population. So to find an interval, we deal with a margin of error. We take your mean, and we add or subtract some kind of number. We call this number the margin of error. So like usually in the polls, somebody will be ahead, say 41% of the votes, and they'll always say a plus or minus 3% margin of error. So rather than say, oh, Hillary Clinton is exactly 41% of the votes, based on the samples that they do in polling, they have, what's the polling for the, Nielsen is the TV. What's the polling one? The Gallup or something like that? Gallup polling, where they do for the voting? I just lost the train of thought. So whatever it is for your polling. So rather than say she's exactly this, they'll drop it 3. She's anywhere from 38% to 44%. And that population mean should fall in between there. We have a better chance of hitting that there. So they always usually give you a plus or minus on the polling, which is why two candidates can overlap. Okay, they can overlap at some point. So to do this, we like to look at the graph. We're going to put these on a number line when we start. Now I want you to notice this. This is your point estimate. This is your X bar. We make your sample mean be representation of your population. We have no other point estimate. Notice from here to here, this is the same distance from here to here. This is your margin of error. Added and subtracted off your mean. So we take your mean, we add the margin of error, we take the mean, we subtract the margin of error. We have a number of ways we can write your interval. One of the ways we write it is just like that, 27.5 to 31.7. There's your interval. We can be confident to a certain extent that your population mean will fall between these two numbers. This is the most important part of your interpretation, guys. We know this is your sample. We found your sample mean. By making an interval, we want to be confident to a certain extent that your population mean will fall between those two numbers. We're making an inference about your population from your sample. Okay? Okay. Just so that you kind of get that part. A level of confidence is what we look for too. We want to be a certain percent confident. I want to be 95% confident that this is going to happen. I want to be 90% confident. I want to be 80% confident. These are the general ones that we find for confidence. Now, again, where do I get this number from? Your level of confidence comes from here. Your level of confidence says 90%, and we've done this part before. 90% sits in the middle. And we found the z-scores that sit around the 90% when 90% falls in the middle. We said this whole area is equal to 100%. So if 90% is in the middle, what do these two pieces have to add up to? 10. Therefore, what is this one piece? 5, and this piece is 5. They both have to be equal. This is symmetric. So we do an inverse norm for 0.05. And this is where this number comes from. You're going to get a plus and a minus. Okay. So since it deals with a critical value, your plus or minus, we generally say positive, so we don't have to say plus or minus. And it works the same for these guys. If this is 95% in the middle, 95 goes here. These guys add up to 5%. So this is half of 5%, 2.5%, 0.025. And we do an inverse norm on those. So if I asked you 80%, and keep this chart handy, and we keep adding to it when we use more. So if I asked you 80%, and 80% fell here, what do these two tails that are symmetric have to add up to? 20. So what is 1? 10. So if you do an inverse norm on 10, what number should you get? 1.28. Okay, we've done these before, right? We've done these before when we did those percentage things. So that's how we look for our critical value for this stuff. This is really, really important. And as you can see, what happens to this z-score number as we need to be more confident? It increases. So if we multiply something by a bigger number, it's going to be a bigger result, right? So our plus or minus is going to increase as our z-score increases because we want to be more confident. We want to make sure that we know exactly where we're supposed to be. We give ourselves a little bit more wiggle room, so to speak. Okay, so again, we found your area. That's how we found your area. Now, we always end up with some kind of sampling error. A sampling error is the difference between the point estimate that we did for your samples and the actual, in this case, the population mean, the parameter error, the value. Your parameters can be mean, standard deviation, variance, can be any of those. Right now, this unit only talks about mean right now. So there's a chance that we have an error, and our sampling error would be the difference between those two actual values. Okay. I know I'm kind of hitting the points, but as soon as we put this together, it'll kind of make a little bit more sense. Your margin of error. This is your formula for margin of error. Your margin of error is the greatest possible distance between your point estimate, in this case your sample mean, and the value of the parameter that it's estimating. This is where your wiggle room comes from. This is where your margin comes from. Your value, your point estimate will be here. Right now it's our mean. Our margin of error will go out here and down here. And we have a nice little formula to calculate margin of error. Now, the nice part about this, it is getting a little bit more difficult, but I will give you all the formulas. I expect you to know your z-score formulas and the means that we've been doing, but when it comes to these guys, I will give you the formulas. Because to me, memorizing these is useless. I'd rather you understand how to use these. So when we talk about your population mean with the sample, I will give you this formula. This is your critical value z-score thing that we just saw the chart for. This is your standard deviation. And when we deal with a sample, don't we take the standard deviation and divide it by the square root of n when we deal with a sample? So it kind of will make sense. You'll see all these things kind of pulling together as soon as we can pull this together. So these conditions have to be met. The sample is random, and at least one of the following is true. The population is normally distributed. They have to tell us normally distributed, or the sample size itself has to be greater than or equal to 30, which we did this already before too, when we did the other parts. So we knew in order for us to use any of that sample information, they had to tell us that the population was normally distributed so that our samples were automatically normally distributed, or our sample size had to be greater than or equal to 30. So let's see what this makes. So from example 1, in example 1 you had to put this all into your calculator. You had to find the mean, you had to find the standard deviation. Okay, now you want to say that n is greater than or equal to 40 so that we know this is normally distributed. Because n is greater than or equal to 30. So we're good to go with this. So we want to find the margin of error for the mean of hours worked by the grocery store employees. And we're also going to build this confidence interval at the same time. So we're going to assume that the population standard deviation is 7.9. Okay, so they gave us this. We didn't have to find ours. We just had to find the mean. All right, so now all you have to do is put it into this formula. ZC comes from your table for 95%. So say we don't have our table handy. We say in between here is 95%. These add up to 5, so this is 0.025. I do an inverse norm and 0.025. Or you can go to your table right now. I'll give you the table as well. But if there's something on there that's not there, you're going to have to figure it out. So what's the one for 95%? 1.96. You're going to find the 90% and the 95%, the ones we use the most. You're going to put this in positive. It actually doesn't matter if you put it in negative because your margin of error is a plus or minus anyway. So if you minus it, then you're also going to plus it. But just keep it positive so we get your formula going. Your population standard deviation divided by the square root of n. How many was in our sample? 40. This is your margin of error. So your margin of error works out to be 2.4. What you want to do is keep your margin of error the same decimal value, the same decimal places as the mean. And this is why. Because when we build your margin of error, plus or minus your mean plus or minus your margin of error, we want them to be the same. So we're going to say x bar plus or minus 8. 29.6 plus or minus 2.4. This is going to build your confidence interval so that you can be 95% confident that your population mean of all the hours worked by all grocery store employees will fall between these two numbers. So you subtract 2.4 and you get 27.2, and you add 2.4 and you get 32. We're building a margin, we're building our interval at the same time. They go back to it, but we're already here. So on your number line, this is what it looks like. Here's your 29.6. We go up here to 32. We go down here, equal distance to 27.2. This is the most important part. We will be 95% confident, because this is the part they told us up here, that our population mean number of hours worked by grocery store owners will fall between these two. Not our sample, we put our sample there. We do this so that we make an inference about the population based on your sample information. Now, if I did all this work and I found my mean of all my sample means, I did a great job. I took a lot of samples, I did their means, I calculated the mean of all the means, and it came up with this. If I then was able to poll the entire population, what are my chances that I'm going to hit that exactly? That one number exactly. Pretty slim, right? I mean, even if I did this, I took samples in here of 5 people each, and I asked you what was your last test average. And I took all those means, and I averaged them all together, and my mean came out to be 83.2. If I asked every single person in my population what was their test, and I averaged it up, what are my chances that I'm going to get 83.2? Pretty slim, isn't it? So if I give myself a little wiggle room, that's my margin of error, my plus or my minus, when I have a better chance of my population falling between those two numbers, that's what a confidence interval does for you. It allows you to have more than one number to hit exactly. It allows you to fall in between these two situations. So when I build my confidence interval, I'll subtract my mean and I'll add my mean. Okay? And now I'm making an inference about my population that my population mean will actually fall between these two numbers. Yes. Yes. All right, let's build another one here. In Example 2, a try it yourself 1. They had us take the mean of that try it yourself 1. I didn't have you do it. So I will give you the mean. The mean was 28.9. Okay, so now we're going to build your margin of error and your confidence interval based on a 75%. So we're going to say, so 95%. We're going to say your z-score times your population standard deviation over your square root of n. Okay? So we're going to say z-score for 95, right off your table. Didn't we just use that one? 1.645. Do you remember when every time we did 1.64 and I said, well, this is the one we call it 1.645? And I said, you'll see why pretty soon. This is the one that fell halfway between. So they do list this one as 1.645. They said use your standard deviation and divide it by the square root of n. And we had 30 in your sample. Your sample contained 30. So n is greater than or equal to 30, so we know we're normally distributed. We know we can do this. So this builds your margin of error. So put that in your calc and give me your margin of error. What do we get? How many decimal places should I round it to? What's my mean? 1. Go to the mean, because we're going to do the mean plus or minus the e anyway. So round it to the same as your mean, whatever your mean happens to be. If there is none when you do your mean, then go 3. But for these guys, we'll probably be doing 1. Anybody come up with the value? 2 point, you got 2.4?
Yeah, around
2.37?
It's 2.37 around.
Oh, I'm sorry, this was my fault. I put 1.645, wasn't this 1.96 for 95? Yeah, that's my fault. I was saying, I was trying to remember to tell you this is where the 1.65 came in with the extra decimal, and I ended up putting that. That's my fault. Oh, so, okay, so what? 1.645 was a 90%. And what was that margin of error? 2.4. And what's this guy? 2.8. So when we needed to be more confident, look what happened to your margin of error. It got a little larger, right? I want to be more confident that this is going to happen. So give me a little bit more wiggle room. I have to make sure that it falls, that I represent the population fairly. So if I need to be more confident, I need a little bit bigger margin of error. My mean is not changing, but my margin of error will. So we take this, your mean, and we plus or minus 2.8. We're building our interval. They didn't tell us to, but we are. So our confidence interval then says, subtract this and add this. So here's my interval. Instead of guessing 1 point, 28.9, I can represent my population. I can be 95% confident that my population mean will fall between these two numbers. My sample mean is already there. I put my sample mean there. But I'm estimating my population. Now, here's where I like the calculator. Your calculator has a very nice thing for this one. I just got to find it. Go to stat, go to test. I'm doing an interval, right? I'm doing a confidence interval. I need to look for the word interval. And I'm using a z-score, right? So I need to find the guy that says z interval. Right there. Number 7. it says, do you want to use your data or do you want to use your statistics? I'm just going to use my statistics. It says, give me your population standard deviation, 7.9. Give me your sample mean, 28.9. If I wanted to, I could use my data and put it in my L1 and let it take it out of there. My N, how many did we say was in this sample? 30. And what confidence level did we want to be? 95. Now, once I do this, it returns my interval. See my interval? 26 point, this over here. 26.1, this rounds to 26.1, and 31.7. See it? So it gives me my confidence interval. What it doesn't give you is your sample mean. Was there any place I could put my sample mean? Yeah, it gave my sample mean. Now, it doesn't give you your margin of error. Okay, so I know my margin of error is the difference between where my mean falls and any endpoint. All I have to do now is take this and subtract my mean, and I will get my margin of error without having to use my formula. I don't even have to use my margin of error formula. I can work myself backwards. That's why I love the confidence interval on this. Number one, it's statistic, it's a test, and it's labeled interval. And it'll give me the interval. I can subtract my sample mean should fall smack in the middle of this. I could subtract it, or just minus this side, and I still get my margin of error without me having to calculate it. I don't need to know the 95% code. I don't need to know the 80% one. I don't care. My calculator can do that for me. I do like this one on the calculator. If for anything else you guys didn't use the calculator, this is a nice one to do it on, the intervals. You bypass this whole thing. You bypass everything. You come right to your answer. And subtract your mean off of this, and you get your margin of error. It's kind of a nice one. They do go into building your confidence intervals, which we just did. We just built your confidence. Another way they write it is this. So if this guy was 28.9 plus or minus 2.8, you could write it and separate it out like this. 28.9 minus 2.8, less than your mean, less than 28.9 plus 2.8. And you just have to add these values. 26.1. The one nice thing about writing it like this is your population mean is sitting there, not your sample. So it tells you you needed to be 95% confident that your population mean, this is why you did all this work, that your population mean actually falls between those two numbers. Nope, because what I can't ask my whole population. So I take my samples.
So why are you using you?
Because this is my inference that I make based on my sample.
Okay.
I took my sample and I subtracted my margin of error.
Okay.
So now I expect my actual population mean. Could I do this? I would expect my population mean to come between these two numbers. Instead of hitting it on one exact number, if I said I expect my population mean for this number of grocery store employees, hours worked, to be 28.9, if I ask every grocery store worker in the United States, it's very, very rare that it's going to come out to be exactly 28.9. But if you do this from 26.1 to 31.7, I have a really good chance, 95% confident that my population mean should fall there. This whole thing is based on an inference from your sample to your population. Okay, that's all we can do is make an inference because we don't know enough about our population. So again, these are your steps. We're going to verify that we know your standard deviation for your population and that this is normally distributed. We're going to find your mean, put it in your L1. I would just put this in my L1. This is add them all up, divide by how many there are. Find your ZC, look at your table, figure it out with your graph, find your margin of error, and build your interval. That's it. That's exactly what we did. And then we're going to interpret. What I want you to do here is add this. You're going to interpret your interval. And I want you to add this little piece. Let's just call this N% confident that the population, put this in your note part, mean will fall between these two numbers. N% meaning 95%, 90%, 80%, whatever confidence level they give you. You can be 95% confident that the population mean. Underline this guy. I reinforce this because everybody usually says sample mean. You know what your sample mean is. That you were able to find. It's your population mean that you couldn't find. That's the one you make the inference about. Good so far? Okay. Let's give you some.